All right. Hello, everyone. I'm Saud Alam, a PhD student. I work in Web Science and Digital Libraries Research Group. I also happen to be Docker Campus Ambassador for DU. And today, we'll be going through a walkthrough of Docker and how you can use it to containerize our applications. My display is not mirroring, so it's going to be a difficult ride for me. But we'll go first with a short presentation and then walk through code illustration. All right, so while you are being seated, I want to start with this story. It was in 2016. I was in New Jersey for a conference. There is a tool called Archive Spot that we use in Web Archive related content analysis. It's a very interesting tool. However, setting it up is a pain because it needs Hadoop, it needs Spark, it needs cluster of multiple machines. And putting all those things together with notebooks is really difficult. I tried to set it up multiple times, but thus documentation was not adequate, and I just couldn't figure it out how to work that. So in that conference, I met the guy who actually wrote this software. In the lunch break, I asked him, hey, could you please sit with me and tell me if I'm not willing to run it in a cluster environment, I just want to run it on a single machine. I have a bare bones Ubuntu machine, tell me what I need to do in order to run it. He sat down with me, and he gave me instructions, okay, do this, install this, configure this. I wrote down all those instructions, but not in plain text, in a Docker file. The lunch break was over, and we started the afternoon session. I built an image, pushed it to Docker Hub, tweeted about it. While the session was on, people started testing on Linux machines, on Windows machines, on Mac machines. A very complex software that was very difficult to configure. Between just one single command, you can run that and you get it all running. So that motivated me, and we started Dockerizing almost every single software that we write in our lab now. And this whole story is available in our blog. Now, let's move on to some problems that we researchers and software developers feel almost every single day. You know about magic laptop problem? When you go to your professor and you are supposed to demonstrate your assignment, he didn't work on that machine, and he said, he was working on my laptop. That's your magic laptop. And this problem is called magic laptop problem. So, you attended a conference, someone demonstrated a very nice tool, you came back home, downloaded their code, tried to run it, it didn't work. What was wrong? Perhaps they did not document it how to run, what needs to be configured, and other things around that. Some other problems. You installed a software that needed Python 3. But you cannot upgrade your machine's default Python version to Python 3 because there is another software running which needs Python 2. And this is a general class of problems that we face all the time. Again, you want to contribute to some projects, but it's a mess. It has all HTML, PHP, Node.js. You name 100 technologies that are all available in a single code base, and you're not an expert on some of those, so you cannot contribute to that code. Another problem we face, over the time we use our machine, we customize it, it works for us, very nice, and then time comes, we change our machine. We install necessary software, and then we realize, this one is not working. Oh, I forgot to install that other thing that was needed. So, and if you are a system administrator, sometimes having too many VMs to solve such problem is another level of difficulty. So we have some real issues in Web Science and Digital Libraries Research Group. We all have our own desktop machines, but we also have about 15 or so virtual machines where we deploy our applications. And why it is the way it is, because over the time, each researcher was using their own technologies and tool sets to solve their problems. And they would come up with a service. But they did not want to step over to someone else's machine configuration because they needed to install certain software. So we request root, hey, please give us a virtual machine. They will configure a virtual machine. Now, we got a pile of virtual machines. Every time there is a security bug, and those machines need to be upgraded, it's a very difficult thing for systems group and for us to keep all those machines up to date. So I hope these are enough reasons to consider, to look for a solution. And the solution that I'm introducing today is Docker. What is Docker? It's an application containerization platform. So how it works, you have your host operating system, it could be Linux, for example, and you have a thin layer of injection that is called Docker engine. On top of that, all the applications that you write, all the binaries and libraries that you need, you package them together and you run them. So now there is one container, there is another container. They can talk to each other if necessary, but they will not step over. They are in their own isolated environment. And all those processes will still be running on host machine. They are just separated. And the way you go about it is you first write a Docker file, which is a set of instructions to start from this configuration, add these files, install this software, change these files, all these step-by-step changes. You write in a Docker file, and you build it. When you build it, you get a thing called image, which is a template of that whole package thing. When you run one instance of it, that is called a container. And you can spin as many containers as you want from the same image. So if you have a software and you want to run it 20 different instances of the same thing in your research project, you can perhaps build one image of it and run it on multiple machines or a single machine with multiple instances. So Docker uses a tool called AUFS, which is a union file system basically. And the way it works, you start each layer in your Docker file, each instruction adds one layer in your file system. And say your images base layer has file 1, file 2, and file 3. In the second layer of instruction, you basically updated file 2, you changed it to something else. And you added another file 1, file 4. In the second layer, you got updated file 1, but removed file 2, file 3. Mind that this is not deleted from here, it's just noted there that this file is deleted in this case. And then you build an image from this. So you got a stack of files. When you run container, it loads, scans top down. So file 1 will be read from here, this one will not be reflected in the container. File 2 will be there. And file 3, although it is available in the lower layer, but there is a cross mark where this file is deleted, it won't be available in your container. And so on. Container itself can have more files, like file 5 was introduced in the container. It was not part of the image. So, moving on to the script. You were scrolling around on the internet and you got this nice little script. Looked at it, it looks like it's taking our argument, passing through uso, and extracting names from there, the extract attributes. So a simple thing, like you run this script and you pass a URL and you get all the hyperlinks in that web page. This is what this script is doing. However, if you try to run it on your machine, you can run multiple challenges. First of all, you're trying to execute it, perhaps it was not set as executable, so you need to prefix it with something else or change permissions. You don't have Python installed on your machine. Even if you do have Python installed, you need to add more libraries in requests in Beautiful Soup that are not part of the standard package. But in order to install those, you need to install something called get. So if you go through all these processes, then only you will be able to run this simple little script. How can we change this script? We can write all those instructions in here, in this Docker file, and we are saying we want to start from a base image that has written official Python packages. Added a little bit of metadata in there, and then I say we want to install Beautiful Soup using pip install and the same way request. And from outside, we want this link extractor.py file. We want to copy it over inside of the image at app directory. Then we are going to change the working directory and changing the mode so that the file is executable. And then we make this entry point. Once you have this Docker file and you build an image from this, you should be able to very easily run it something like this. Docker image build, and you give a tag, dot is the current directory, it will build the image, it will package all those layers in there, and then you can run Docker container on whatever was the name of your image, followed by the URL. It will run a container, execute the script, give you the output. So the cool part here is this. Now you can push this image to Docker Hub the way you push code into Docker GitHub. And someone else from somewhere, they can run the same command that you ran. They don't need to build it. They can run this command with another URL, and the Docker will check if this image is available in their machine. If it is not, it will check the Docker Hub. Since I pushed that image there, they will be able to pull it down and run it. And the single command that whole script will be executed on their machine. So now I move on to a small demo. And that little script that we saw, we'll try to move it step by step, and then make it something like this. Then we'll have a PHP application, which will give this interface. But in order to extract links, it will ask the Python server, it will be acting as API. That thing will get the case from the library, but first it will check cache locally, and if it is available in cache, it will serve from there, otherwise check from. So in the 1, 2, 3, these three components will work together. At least this is what we are trying to build here gradually. So I have that file that we demonstrated, and this is a basic Ubuntu image with nothing in it. And if you try to execute this thing, it will fail. So we can change permission. And then we can try again, where it's saying Python is not available. So now you go ahead and do apt install Python, take a while to install that. And try to run it again. We got another problem. Request is not available. So you need to figure out how to install request, and it is something called, but pip is not found, so I need to go back and install Python pip. So I'm trying to demonstrate that the kind of pain we'll go through with that simple little script that we saw before we can execute it. any questions while this is on? Yes. So now we can try to it again, but the request library can be installed now because we have it. So we execute again. We got beautiful soup missing. And after all that, perhaps we'll be able to do something like so it did extract the URLs for us. So, but some of those URLs will be just paths, so you'll see that. So after this phase, although I knew what the steps needed to be done in order to perform this, I'm going to exit from here. So now we'll try to do the same thing with Docker. We got this file. We are going to get check out step 1. So that was step 0. And now we have some more files. The Docker file and the link extractor can actually show what's in there. It's just those instructions that I demonstrated in the application. So now I'm going to build it. And the file has an instruction how to build that. So we build the image, and now we can run it. So we didn't have to do anything installing all those things because our Docker file did that, and we can run it for any number of URLs we want. /review.eu, and we'll get this list of URLs. But the problem is still there. The URLs are not complete. Some URLs will be complete, some won't be. So how we can fix that? And for that, I've prepared another thing. Get check out step 2. So now this Python file I have made some changes here. Rather than insert everything here, I made a function and which basically extract URLs and joins with the base URL, and not only extracts the URL, also extracts the text that is hyperlinked basically. And it creates an array of objects which is then printed here. So going through this route will make it easier to use it as a module. And if you go build that image again, So since I have already built this, so this is happening very quickly. But you see, on each step, it's putting those layers basically. Working directory change here, added this thing, all these things, they are using cache because I've already built it once so that we can speed up the demo process. But otherwise it will take a while to run. And this time, we run from the step 2 image. We'll see that the URLs are coming full, and they also include the text, and all those URLs are they could be from the same domain or elsewhere. So this is improved. Now we are still working with a single script. So we are moving on to a little more complex structure. Here we have modified the Docker file a little bit, added this main.py, which will run as a server. Now, it will use the extractor file as a module. So if you look at it basically, and rather than installing individually dependencies into individually added requirements.txt, which is how Python people do it, and then we are running all the requirements from that requirement.txt file, copying every Python file inside, changing the permission, and running main.py as the base command. So if we run this, we should have instruction how to do this. So we build the image, and so let's talk through what is this command basically. What I'm saying, hey Docker, run a container, and map port 5000 of the host machine to port 5000 of internal container, because our server is going to run on port 5000. We can change these mapping as needed. And this IAT are infected terminal so that it maps to our TTI outside, and that RM is nothing but remove the container once I'm done. And then I'm specifying which image to run it from. And when I run this, let me copy this thing. Because now we are running a server, and we can So the server is running the container there, and we can talk to it, and the response is now coming in JSON format. Because the server that we wrote, it internally uses the module that we wrote before, and converts that into the JSON format. So you can check in the browser or anywhere. You can kill this process now, and move on to this was step 3. So we'll move to step 4. Now a few things have changed. I have introduced a new file called Docker compose file, and all the Python files that we saw before, they are now in API directory. So here, Docker file, link extractor, main.py, come there all onto another separate directory. And in www, I have an index.html PHP file. But if you look at our compose, so here, so this is a new tool that I'm introducing, Docker Compose. It's also an official tool. You can do everything with Docker. But what it does is it allows you to describe your all those flags like map this port, mount this volume, all those things in a very descriptive YAML file, and then use this tool, which will then run those containers. And if there are multiple containers, it will try to link them together and create all those networks. That you can do all manually, step by step. So here, we have defined two services. One is called API, which will build an image on the API directory. It will map the code 5,000 to 5,000. However, the web one will use standard Python's, PHP image, which has Apache built in, and we can check. I will show you how to find these official images. And port maps 80. Now we know the API is running on port 5,000, so we'll let this web application know where to talk to get the JSON file. And we also mounted this www directory inside our www and HTML of this image, because we know that Apache by default checks files from there and serves that. So now if we want to run this, to do Docker compose. So it has very close images, and now it is running one instance of web and one instance of API server. And all those logs are shown here. So I should be able to do here. I can go to look at this now. And we should see this example. So this is coming from the PHP thing, which will internally talk to our, and let's say, we want to extract these from this page. Gone through and not only extracted all the links here, listed all the links. So this information is coming from the JSON API, which is running in Python, and also analyze how many links are from Google, how many from Twitter, and so on. So this is what this application does. So right now there are two there is an API and there is a web service, and we want to change that. So we fill this process. And so not a lot has changed, except we moved, we made a Docker. But initially we were running the main PHP image and mounting our PHP file inside. But then if you want to run it somewhere else, you need to give these PHP files as well. But this time we built an image for the web thing, another image for API, and we'll run both images. Plus there is another change that I made here, which is if you do readme, see there is we have started using Redis now, and that can be seen in the compose file. So this thing is as before, web now builds image, not just mounts from the official image. And the entry point has changed already. And we have used another service here, Redis. And we don't have to provide any configuration because the official image is self-sufficient. You can run it unless you want to change certain configurations. You can make a derived image from that. So this time when we run this, all three components will run. And we should benefit from the caching. So he tells you how to build, which is before. So now it has web running, API running, and Redis instance running. And we should be able to go and check the same thing again, you won't see any difference here, but trust me, it has become faster. And there was like an 10x speed up or something, especially the sites that are hosted far. I can actually check on the API and run it and see how long it takes. So now what it does is, when it receives this URL, it checks whether we have it in our Redis cache. If we have it in the Redis cache, it will just take the response from the Redis cache and return it. And Redis is in memory cache, so it's quite fast. If it is not there, it goes, downloads the web page, processes it, creates the JSON, puts it into Redis cache, and returns the response. So that's how it's working now. So the point I wanted to illustrate here how easy it was. I mean, leave the coding aside, what we did in PHP, what we did in Python. But putting these three things together was not difficult at all. Just, this is what I did. It is all my Python file, all my PHP file. We built images from there, put them together, and we also added this. I have this Python file now. The code has changed to utilize this basically. And all this code is available on GitHub, so you can at least go and see what's in there. And this is the last step I promised. So something has changed here. We don't see any Python file anymore. This remains the same way. This API now has a thing called gem file and link extractor.rb. So the thing that we built in Python, I rebuilt the same thing, the API server in Ruby. Why? I don't know. Perhaps sometimes you need to reinvent the wheel, or you need to make decisions. A new developer came to the team and said, hey, we need to go to the Node.js side. It's awesome. Okay, let's try that. So because this whole thing was component-wise, not everything was put together, we were able to replace just this piece in a different technology, as long as it promises to give the same request and response mechanism. This is exactly what I did. Replace the Python with Ruby. And if we look again, and if we have no, so not having any surprises there is a good thing. It still works the way it should be. So now it's running. Nothing was changed on the face. The PHP code was intact. Nothing was changed. Just the API service was replaced. So this composability, where you go to microservice architecture, where you make small components put separately and let them talk together. Teams can manage one piece at a time. As long as they're not breaking the promise, they can change things. So there is one more thing that happened here. And let me just check that. You did it a few times. And I'm going to do this. All right, so this is something that I added in the Ruby implementation of API. It was not in Python, but we also added logging mechanism. So it says at this timestamp there was a request for this URL which was missed. It was not in cache, but in subsequent requests it was hit. And then we got this one. It was a hit because it was cached in the previous Python version as well. Because Redis cache was being used at that time and we did not clean the cache later. So that's why you see it here. But at that time, it was not locked. If you try another URL, that would be misleading. So another point I wanted to show here is file. Our data, there is a thing called volumes. And it is when I say in the current directory there is a directory called logs mounted inside the application in container at this location. So what happens otherwise? Containers are self-contained. They run their own life cycle. Is like once they are done, they're done. Nothing remains. Like you package everything, you roll it, and they will run as long as they run. They're killed, everything is gone, that is there. But if your process is producing something that you care about, databases, for example, or in this case, log, you want to mount some external drive inside, and that will not be part of AUFS. So those files will be written, and you'll be able to see outside. So that's what happened. Those logs were written inside the container, but since I mounted from the outside, the file was available outside, even if the container was gone. So that's all I had for the demo. So if you want to so you go to this repository, and all these steps that I described, they are in step 0, step 1, 2, 3, 4. Step 0 is the one where you found the script somewhere online and you wanted to run it. You have no idea how to go about it. And then it improves upon all these directories have readme files you can go. So if you are here, for example, it will tell you what has changed from the previous step, and to try it out, what you need to do. You need to run this command, you do this thing. So all these steps are documented here. And I'm using a bit of trickery here to demonstrate these things. I'll stop here and take questions now. Good questions will get t-shirts.
Good question.
Yes.
I noticed that you have in one of the commands that remove the container. So my question is like, if you don't do that, are you going to be creating a bunch of containers that eventually are going to fill up your memory or hard drive, or okay, that automatically get broken?
So a few things that I did not show is I just wanted to demonstrate the concepts and not necessarily showing everything. So Docker comes with a lot of commands specifically. The whole set of the commands here. And some important ones are Docker image ls. It will show you all the images that you have in your machine locally cached. So when I was saying link extractor is step 1, colon, this is the image that it was using. If it was not in my machine, it would try to find an image called link extractor with tag step 1 in a repository. But in this case, we built locally, so it was available locally. And if we want, we can push these images to have. Internal layers are not shown here, but if you do -A, you can see a bunch more. These are none, they are not tagged, because when you build this, you had like 3, 4, 5 different layers in the Docker file. All these things are coming from there. They are all content addressable. So another command here is Docker image containerization. So right now it's showing nothing. You can do -A. It will perhaps show some images that we ran, but we did not clean or remove, so they are still lying around. And you see here, it was created 6 minutes ago and exited with 0 status code. Okay, so these containers are still there. You can restart them, you can latch into them, and if there's any file you want to save, you can bring it. However, if you remember what I was doing --im flag when I was running them. So that flag tells, when I kill this process, please remove this container. So that way it keeps me. However, over the time when you run services like that, in background mode, there will be a lot of containers that will pile up over time. So the way to clean up is you do Docker system df command. This will show you how many images are there, how many containers, how many local volumes, and build caches, the total, how many are active, what is their total size, and if you want to clean them, how much size you will save. So, and then you can do Docker system prune, ask you, do you want to clean all these things? You can say no. That. So periodically you can just call Docker system prune and it will be harmless, will remove unnecessary things that are piling up. Plus pruning options are also available in images, separately container, volumes, networks. So Docker has really too many top level things. There are images, those are layers and layers of files that you put together. Containers are when you run them. Network is you can make like network, and so one thing that I did not describe was when we were using Docker Compose, it was creating networks for us. Temporarily, it was creating a network, and there was an overlay network, and all the services described in the Docker Compose file, they were part of that network, and that's how they were able to check each other, ping each other, or access each other. Docker Compose was doing this all behind the scenes without us telling it to do. We can create Docker network beforehand and ask it to use that one instead. So in our Docker deployment that we have on our where we run Navigator and other things, we have a thing called proxy, and we have created a custom network for that. So every time we want to add more services to it, we just ask those services to use that network so that the proxy can access those new containers. That's what we use that on. Yes?
So, you explained a lot about using web servers and using it on a single server. So how do you prioritize a Docker container over others or limit it for like computationally expensive tasks?
Okay, so obviously I did not talk about clustering. I did not talk about there is a thing called Swarm mode, where you can create Docker Swarm and add machines to connect to that Swarm, and they will become part of a massive network that you will make. Docker will manage communication between them. You can also specify services like, hey, this new machine that I'm adding to this Swarm has 8 gigs of RAM, but has very fast SSD attached to it, this much storage, and is available in this region. You can specify all these properties, and in your Docker Compose file, or extract file they call it, you can specify how many instances you want to run for a specific service, and what conditions you want to match. Run this service only in this region where there is like high memory instances or something. You can specify those conditionals, and Docker's Swarm Manager will take care of that. And if you have said, I want 10 instances of it, and if there are 12 different machines connected to that, 5 of them match the criteria, it will distribute 2 on each. But you can also specify the spread policy, like how it's going to choose machines. And one of those machines, when it goes down, the manager node will take care of it in instance, create other instances. That's right. So whenever you create, this microarchitecture style thing, always try to focus on making your containers as self-contained and stateless as possible. So if you were to kill 5 of those, it doesn't harm you. You can anytime put more containers and then just join and work from it. So for example, if you had 1 million URLs and you wanted to download all those things, you don't want to divide like, hey, top 10 links, you run 10,000 links, given to that. You can put a queuing system somewhere. So any container independently can go check what is next in the queue, give me that, and you will download this image. So that way you can have like one service working or 10,000, doesn't matter. Yes. Looks like these guys are taking all the t-shirts here.
So when you showed your images on the various sizes, a lot of them were 700 megs or 800 megs. Those two looks like. Yeah. Then when you did Docker system DF,
right.
So they take images and size, approximate size 1.4 gigs. Now, if you sum all of this, they definitely make sense.
So that is the beauty of AFS, and that's why you put things in layers. So for example, I got Ruby or Python or something. They all start with the base image, say Debian or something. Okay. So their base image, 10, 20, 30 layers that were used in creating that base image, those layers are common. As you put more and more layers on top of it, any common layer will be stored just once because it is content addressable. Okay, so you create new branches only where something changes and you don't have any matching thing there, and that's why the sum of this is a lot lesser. That's why Docker uses AFS, and that's why you can run like thousands and thousands of instances or containers without consuming too much memory. So if your container does not create any extra files or anything, it will not even create any extra layer. It will just use what was the images layer that it's running on. Yes?
So you show us the Docker file, which is easy to send to someone and recreate the same image and do whatever you want. But what if you create the image, you create a container, you generate some data, and now you want to pass this exact data to someone, continue doing what you were doing at some point?
So this is a very interesting question, and it is actually being appreciated in research community a lot, where they want to reproducibility, and this is we review research papers all the time, and they come up with the results, and we just believe on them because running their own research on our end would be costly, and it will warrant a lot of time. So in this case, if they can package the software, they don't have to write down steps like, hey, download this file from here. They can just write all those things down in a Docker file and allow us to run those same things and to run the same. So you can put like terabytes of file inside the container. There is nothing that stops you from doing that. However, if you can keep it somewhere outside, you can always duplicate or in whatever way you want to access that data if it is available somewhere publicly. It is not wise to make images terabytes of size, at least for now. A decade from now, perhaps the situation will change. Yes.
So, how have you seen Docker used with other containerized components like Pachyderm or something to that effect, where it's acting as a computational agent on one side, accessing a containerized database on another? Have you seen something like that before?
I'm not sure if I could follow your question, actually.
Okay, so are you familiar with Pachyderm? It's basically a containerized data center.
No, I'm not aware of that.
Okay, then have you seen Docker? How does Docker commingle or communicate with other containers? For instance, something to the...
Okay. So what I'm aware of is Docker has created a thing called runc, or there is a, which is their implementation of running containers, but they made this standard available, and I think it's part of the native compute native or something. What's the CNC compute native cluster or something? So there is an organization, basically a third party organization. So they donated this whole thing there so that other container implementations So there is Rancher, there are other platforms like, Google has a thing called Kubernetes, which is another orchestration platform. Docker has a built-in swarm mode, but they do similar things. And because this basic core thing is abstracted out and standardized, so others can play around. In HPC community, I came to learn that they use something called Singularity, so Docker is usually run, the images initially spawn with the root privilege basically. You can specify a different user to run as, but the daemon is still running as root. Singularity, however, has gone a different route because in HPC environment they care about a lot the security, so it is non-root by default basically. There are many alternatives out there, and obviously some are implementing their own way, but some are trying to make it standard so that other players can come in.
So how does Docker work with the cloud environment? Can it spawn an EC2 instance?
Yes, so all the things that I did here, I can literally move that Docker compose file, put it somewhere else, and if the code, if I build image and push it somewhere else, then I won't even need to move the code anywhere else. But right now, I can go ahead and create an instance on DigitalOcean and build this thing there, run there, and you all be able to access that link extractor right now.
It's after creating an EC2, right? Like, can I create an EC2 with Docker? Can I create an EC2 with Docker?
So you want to implement
full process?
Okay, like a cluster environment. People are using PaaS and SaaS and other things where they're utilizing Docker or something more core than that to provide some services like that. There are services that would allow you to run, for example, specific applications of, say, WordPress. So you don't have to install yourself. Hey, go fill your name here, and we'll create an instance for you. Earlier, they were using virtual machines or LXCs, but now they are moving towards using Docker for providing such services. So yes, it is doable. There is a project called so if you go here, training play with Docker. If you just go to play with docker.com, that is an implementation of Docker Swarm inside Docker Swarm. So you can actually, without installing Docker or anything on your machine, you can play with their system in a browser, and you will have like multiple machines configured there. They can talk to each other. You can experience that. But each instance is only available for 3 hours basically. So you can play around and then move on. Yes.
So can you create several Docker images in the same folder simultaneously, because the Docker file has a default name, right? How can you distinguish between?
So she's asking, can you create multiple Docker images from in the same folder? There is nothing like in the same folder because the images are stored somewhere else. Docker has a different location where images are stored, but you can ask from the same folder. So if you want to make certain changes of the same, you can have multiple Docker files. And by default, Docker file, the name Docker file will be default, but if you have a different Docker file, say Docker file.production or something, okay? At build time, you can say Docker build -f Docker file.production. So you can specify a new file which has different set of instructions in there, like you are adding some more components or adding some environment variables that are not available in this environment, for example. All those changes can be done. However, there are cleaner ways to do that. You can have the same image, but you can specify things called build args. At build time, you can pass the arguments, and based on those arguments, you can make those images change differently. So when you are building images, you specify something called -t, which is tag, where you name your images. And then from the same file, for different configurations, you can create different images for different images. So let me tell you what I mean. Come again?
I'm talking about different Docker files, not the same.
It doesn't matter. So the default Docker file name is Docker file, but you can have a different file. You just have to, at the time, you have to specify, hey, use this file as a Docker file. And if you read the documentation there, Docker build -h, this should be a flag, okay, file. -f file is the name of the Docker file. Default is tab, which is the current directory, followed by Docker file, which you specify any file direction. As long as it looks like a Docker file.
I think you can also rename the image. There's a
Yes, so for that, if you use the same name for your image, it will override the tag basically, right? So what you will do is Docker build -t my ing. At one time you say my ing, it can be something else, or you can change tagging here, like something for two or something. You can change the name of your image there, and you can specify -f, another Docker file or something. So you can specify which file to use as a Docker file and what name to use. You can change these things. This has a default, this has a default. Yes.
And how do I know what?
We got a lot of t-shirts. There are not enough questions. Yes.
How do you know all the Docker processes that are running and how much of the space each process is?
So when you do Docker container ls, right now it's showing nothing, but let's do cat. I'm going to run this thing. So here you can check on the kernel. Docker and as you know, this API and Redis and web, all those services are running. So 3 services are running, and it is showing you this is the image that is being used, and this is the name of the container. This is the command that is being executed, when it was created, for how long it's up, basically. But you can go further, and you can copy ID or the name, and you can say Docker container inspect. And this will give you a whole lot of information about that container. Where it's running, which volumes are mounted, and how much, a ton of information about that container internally. So there are filtering options. If you're looking for only specific attributes, you can filter that. There is also there is a stats. Okay. So you can do this would feel like the top command that you do locally. This is now showing the process that is running there, how many block IOs, CPUs, and PIDs, and all those. That information is now streaming from the image directly. It's changing over time. So, any more questions? Yes.
Earlier on, you mentioned that that service that you push and pull your images to? Is that the images? Is that the images themselves, or just the build instructions?
No. The image itself goes basically. What happens is like when you push image, then the whole image is compressed as tar.gz file or something, and it sends over. So all these images are nothing but layers of files, okay, internally. AUFS layers, and those are compressed together. So in situations where you don't have internet access, and if you want to move some images from one place to the other, you can actually export and import, like download those images that you have, containers, and then you can import in a different place. And these are just tar files basically. And so far, for many purposes, you will go to a place called Hub. We call it Docker Hub, and you search this. So you wanted to write a code, say in Node.js. You search here, and in most of the cases, you'll find something that is official. That's the one that you want to use. But there are other people who will have their own variations of that. But everything that is not official, that name will have the username prefix. Official images there are a ton of official images for every programming language and other open source projects like MediaWiki or other software that we use on a daily basis. Web servers, they're all available in official images. So if you go to these official images, you will see there is instruction here how to use these images, and there will be list of tags. It comes with a bunch of tags, like this is on build or using Alpine Linux or some other variations, minimal images for deployment purposes. Others would be more. The PHP one has variations for CLI version, for PHP FPM version. There is one that comes with Apache, and I used the one that was suitable for me. So I can just go here and see. And you see all these supported tags. They come up. This one is with Alpine, this one is PHP FPM, but this is RC version. So a very cool thing with Docker is you can very quickly check your software in different environments. So you build something in Java 8, for example, and now you want to make sure does it run in Java 7. You can run an instance of Java 7 in your Docker, put your code inside, compile it, run it. You can very quickly test it, and then you are clean, and it's pretty to come out of that page. Yes?
Yeah, so a little while ago you mentioned that Docker can easily kind of get into the more clustering orchestration side of things. You have that close. So as a developer, when I go off to work with the companies, just how much of the Docker ecosystem am I, as a developer, responsible for? All right, just Docker files, maintain images, is that it?
So usually in bigger organizations, they have this whole setup of DevOps basically. But developers' job is to write code, fix bugs, and there will be testers basically, and there will be operational team which will provide infrastructure. So if developer says like, hey, we want these types of machines with these much resources, it's operational team's job to provide those machines if available. Testing team in the middle will try to check. So usually they have this continuous integration thing. Developers write the code and build the image basically, and push the image to the next level basically, where someone will redo the code or using like scanning of the images for known bugs and security tests and all. When they approve it, in most of the cases these things work in a very signed environment. So all the steps that are there, they want like authorities have private keys to sign to mark that okay, this image is safe, moving to the next stage. And this kind of setup is available. And some of these things are not natively part of the Docker itself, but outside external services. Like Docker itself provides a cloud service basically, which you can pay for and utilize their infrastructure for that. But there are other players in the market who provide it. So For cluster management, for example, resources is another option, but the Google's, what's the name? Kubernetes, yes. That's another good alternative that works on operating features. So, and it's a good thing that not every feature is part of the core Docker, so that things that we don't need, they can be abstracted out. Yes. I won't give you any feature. Anyways, yes. Yes.
What's the main difference between a service and a container?
A service and a container. Okay. So, container is one instance of one running image, basically. Service is when there is a thing called stack. Basically, when you run the container, it is a service, and you can distinguish it from one-off mode. So initially, when I was running commands, when I was passing the URL in the arguments, and the container was giving me response on my terminal, it's all done. It's not exposing any ports, or there is no way to interact with that. I would perhaps not put that in the one-off mode in the service category. But there is another broader category called stack. And stack, basically, when we were running at the end, 3 or 4 different containers were working together, basically talking to each other and giving this whole orchestration. So this whole thing together, the whole package, is called a stack in their terminology. Any more questions? Yes.
So you said that so the containers, can they mount files from outside the system so that I have a configuration file with credentials for a container service running without distributing the credentials inside the container?
Yes. Yes and yes. And there are other options for that. So obviously you can mount country files. You can have outside like your Nginx configurations, for example. You can use official Nginx image, and at one time you say, hey, here is my configuration. Use this, and then it will start dropping that way. But there are 2 more features in there. So sometimes in your applications you need secrets like API keys and stuff like that to interact with other services, like you are interacting your application, interacting with Twitter or something. So you don't want to put those keys in your code directly. So one option is to use it from environment variables and supply as an environment variable, but that is not secure either. What you can do is, Docker has a thing called Docker secrets. And the whole